Good morning. By the way, the dinosaurs did not die from CO2. And yeah, we'll be more serious. Professor Don Wall is a very famous professor, chair professor at the University of Illinois, and no chair is like mentoring chair, and people carry it around. So that's very important professor. Don Wall his expertise is atmospheric chemistry. He started his career. After I got into the atmospheric chemistry a few years ahead, so followed and he later on his leadership in the most recent IPCC 2013 report, the working group for one report. He is one of the two coordinating lead authors. And he also had a lot of work. Fellow for AGU, American Geophysical Union, and AAAS, and also American Meteorological Society. And he shared the 2007 Nobel Prize with Al Gore, and actually I think many of us here. Dr. Wayne Phoenix also shared that. I got a smaller certificate. Without further delay, I would like to invite Professor Wall.
Thank you very much for inviting me to be here. Friends Michelle, many years. Great to see all of you here. We're going to discuss one of the most important issues facing humanity in the next few days. And I feel honored to get a chance to kind of set the stage for these discussions by talking about some of the science outcomes from both the IPCC assessment and the U.S. National Climate Assessment. So let's start. As you all know, the IPCC assessment came out last September. I was accordingly up for chapter 1. And this is the one, so this is the science of climate change, which is 2 other groups. And this is one. But I'm going to make a country in this one. So it's kind of awesome. A number of different groups. I'm going to go through quickly some of the findings from the assessment. But in addition, I'm going to talk about the U.S. National Climate Assessment. And I will but these assessment covers all the way to do look at climate change very briefly and affecting our nation, what the effects in the future of the work that I mentioned that about Andrew Office overseeing entire with the 60 member of the advisory committee. I think it's all about very important part of this assessment is with the so this is a copy of the highlights from the assessment. I brought 5 copies with me that I'll leave for this meeting. And if you look at the previous slide, there actually was the website. You can actually go and see full 870 pages, 40 pages. And it's the only thing we publish. The rest of it is online. But what's online is also very interactive. So that's what I see. We went through an extensive review process. This is IPCC. We went through a public review with an expert review. The government agencies in the U.S. have had a chance several times to review the assessment. And then we had 2 special reviews by the U.S. National Academy of Sciences as part of this. So none of those really changed the message. What they did do, though, was make the message clear. Help us make the message clear. The entire document is intended to be readily understood by the whole public. I like to mention that even the U.S. Congress would understand it. But it really is meant for everyone to be able to access it, understand it, and to see how climate change is affecting them. Now, it is able to be very few people, but the message really applies to all people around the world. So I'm going to go into that more detail. The results. The biggest finding from both assessment is that climate change is not something for in the future. It's here now. It's affecting us now. Climate is changing extremely rapidly. Actually, about 10 times more rapidly than it occurs naturally, based on the analysis looking back at past climate since the end of the last ice age. So very, very rapid. And as we'll discuss, the primary reason for these changes is because of human activity, particularly the burning of fossil fuels. We start, we'll look at the temperature distribution on the upper left, and we see that the temperature has increased about 0.8 degrees centigrade, about 8.5 Fahrenheit, over this time. Much of that change has occurred in the last 50 years. And it's during that time period when we say that the changes to the climate can only be explained by human activities. If we compare that distribution of temperature with the past changing temperature by using proxies, temperatures, ice cores, oil, and look at other numbers for temperature. You look at the red ones are the black are the temperature distribution in the flat. And you can see versus really beyond the temperature that we've seen over this long period of 2,000 years. Most local periods. Well, temperature is not changing. There are many other periods that change climate by temperature. And just looking here, it's also oceans are forming, we're changing ice throughout the world, sea ice, and we're also changing humidity and other aspects. One example is the climate in our ice has been very much faster than we expected from model of sea ice. Large, probably changing sea temperature. The area increase that ups and down from the local climate global, in the market, particularly, if we look at volume increasing year by year. Some of the recommendations around the world, like over 90% of the wages in the world are decreasing, increasing very dramatically. Some of the things the bosses are very greatly, and then running back, most of the changes in energy in your system is actually the atmosphere is small part. And so, it's not great for you actually have some very important atmosphere. But overall, the energy throughout our system is increasing because the presence of this increasing amount of greenhouse gas and we'll bring back and look at that for how looking at it in terms of changing the table temperatures. You see the table temperature increase each people has up, and then by 5 days, the one on record. First question, I can earlier about this. Likewise, when we have 1901 2012, state and orange, yellow, purples are all purples. Are an indication of warming for the planet. The largest one is for the small oceans that are large capacity. And then there's other areas here, really, where we're actually getting and that is because of the melting ice, Greenland, and the Arctic. Because of the fresh water, and then global water. If you look at the station here, it's much, and one of the basic message is that the hydrogen is right. So if you look at the property areas, whereas northern areas of the compounds are increasing on the first part of the class, directly will be expected in addition to that, it isn't just all about warming temperatures and small changes in precipitation. It's really that changes in the amount of severe weather. The system is really these changes in severe weather. Anyway, increasing around the world, like the water here, cold air increasing. More precipitation, I'll show you the basically, the more likely to many parts of the world. Increased recruitment floods on some regions in the U.S. the northern U.S. We're getting large increases in precipitation. And we're seeing crop copies in other countries, including the crop copies, giving less concentration in the fields of crop. Increased activity planting countries is already recurring. We've seen it in the last 30 years, and that is going to further increase. I'm sorry about how sensitive for generally, that's whether continue to change over 20 decades. And some other factors that's really your others, including those scales going, you're not really don't have enough information. However, right now, this first study this shows changing trends and increasing temperature throughout the world. Based on the analysis of units and on the left shows the temperature you get a job on distribution, and then look at the number of what we're doing next decade. You see, that's getting more and more temperatures throughout the world. Overall, it's just going to start. You're still going to keep up. You're still going to think about, but you're not going much. There's much more. In the U.S., we're feeling the effects of the changes in hurricanes, droughts, floods, etc. In all parts of the U.S. are being affected. Now, we can show a similar map. Reinsurance companies have been doing analysis globally and finding a very similar kind of intersection. This shows the changes in heavy precipitation in the U.S. To the analysis we did for the National Climate Assessment. It shows that the top 1% of the events historically in different parts of the U.S. over the last 50 years has been a significant increase in most parts of the U.S., particularly in the Midwest and the Northeast. The only exception is Hawaii. When we had it in 2012, it changed from positive to negative, and it's indicating that communication some interesting behaviors going on in this area. Well, why are we seeing these changes? So far, I've shown you observations. To understand this, you need to go back to the greenhouse effect. It was discovered by Fourier in the 1800s, 1820s, and then substantiated by laboratory studies in the 50s and 60s by John Tyndall in the UK, and then further substantiated since then by many other analyses, including satellites and others, very clearly show what's going on. Basically, life on Earth is, of course, dependent on the sun and solar radiation. A small fraction of that radiation is reflected back to space, but most of that radiation, 70%, is absorbed at the Earth's surface, and we're like any other planet that energy will be re-emitted. In our case, because of the temperature of the planet, re-emitted in the infrared. And if it wasn't for the presence of certain gases, that radiation would be emitted in space. And this would be, of course, the point. But because of water vapor, carbon dioxide, methane, nitrous oxide, and some other gases, a fraction of that radiation is absorbed, re-emitted, and essentially traps radiation in the Earth's system. Essentially, it's like putting a blanket over the Earth. It makes us have life, allows us to have life as we have it now. However, we're increasing the amount of carbon dioxide and methane, et cetera, and that's like adding another blanket. Another fact that the basic physics underlying climate change is really this simple. That the planet really has to respond to the fact that we're increasing the amount of carbon dioxide. Well, we know from many different studies that there are natural drivers of climate change. Every 100,000 years, it's not only the sun, but every 100,000 years we get an ice age. For the last 1.5 years or so. And that's related to how the Earth goes around around the sun, and also the wobbles of the Earth. So that's called the Milankovitch theory. Besides variations in the sun in fact is very stable for many centuries now. In fact, the sun cannot explain the changes we've seen over the last 50 years. The sun actually has decreased its energy, not increased in its time frame. We also want to review, every once in a while we have a very large volcanic eruption that can put sulfur and other gases and particles into the stratosphere. And those can cause a cooling for a few years after the eruption. The last such example, significant example, was placed Mount Pinatubo in 1991. But we also know that humans are important factors in climate change. The graph at the top here shows the increasing amount of CO2 emissions since 1957 in Mauna Loa, Territory, and Hawaii. It's common in many other places. And it's showing that we have this change in CO2 amounts going on throughout the world. First measurements were made, very accurate measurements were made by Charles David Field, gradually developing mine as a Canadian ice. So, I'm very proud of our university. But in those observations, you can see the dripping in the biosphere, which also see this graceful increase. While also the amount of methane is increasing, the nitrogen oxide is increasing, all of these related to human activity. On top of that, particles in the atmosphere are also increasing because of this activity, particularly particles that cause cooling, like sulfur, but also black carbon, which is causing burning. Amount of CO2 currently is about 400 parts per million in the atmosphere. This is way beyond the 280 parts per million of the pre-industrial atmosphere, or the 200 parts per million that would have been in the atmosphere during the ice age. In fact, carbon dioxide decreased during the ice age with the change in the present cycle. That's for about half of the temperature change we see during the ice age. So carbon has always played an important role in our planet. And still does, obviously. And what you see from this graph is that, go back to the last 800,000 years, we are not seeing levels of 400 parts per million. In fact, the last time the values were that high is about 1.5 million years ago, when there was large outgassing of volcanic eruptions caused the levels to be comparable to what we are today. And that was a much warmer Earth in the that took place over a long one, many thousands of years. This is an example of the attribution of climate change. I'm going to show you one example from the IPCC assessment. Go back and look at the period from 1951 to 2010. The increase in temperature is about 6 to 7 tenths degrees centigrade, which is shown above black bar. If we look at the increase in methane and CO2 and nitrous oxide, you would actually kind of overestimate that effect. Because of the forcing of the climate. But it's not, but that change is also compensated by all these particles in the atmosphere, which tend to cause a cooling effect. The net effect is that those changes in human activities can almost entirely explain the temperature change we see over this time period. The natural variations, whether it be internal variability in the system, are due to changes in the sun not explain what's going on. I already mentioned actually the sun decreased slightly during the years. And so it's not surprising that IPCC came to the conclusion it's extremely likely, over 95%, that human influence has been the dominant cause of the observed warming since the mid-20s. While there's lots of other types of analysis we could do with the temperature record, globally and actually a number of many locations on the planet, and find that natural activities by themselves would not explain the observed change. You can do the same thing with ocean heat. The net effect is IPCC came to the conclusion that human influence in the climate system is clear. While building projections in the future, a number of different types of scenarios are looked at. We're trying to look at projections for population, economic development, human choice, and so on and so forth. Only one of those scenarios really makes an assumption of strong mitigation action, and that's at lowest number, CP2.6. The others all assume that the worst could happen just by choices of society. And the highest one assumes that we continue to heavily burn fossil fuels. But that the highest one, CP8.5, that's about 25% of the total source on it being total use of energy actually going to alternatives. So global surface temperature change by the end of the 21st century is likely to exceed 1.5 degrees centigrade relative to the past time period for all scenarios except for that RCP 26. And then that one, we would have to make draconian moves to reduce the emissions sufficiently to be considered very likely. From that scenario, and actually, temperature doesn't stop changing at 2100, even though most of the analysis are only at 2100. Some scenarios have gone beyond that, and suggest temperature, of course, keep changing. But also all the other variables, that sea level rise, et cetera, will also change. The difference between the scenarios in terms of the changes in the planet temperatures, of course, depends on the scenario and the problem. And the largest change is going to be in the and with the largest scenario, we can see changes of 7, 8, 9, 7, annual average in this time period. If you look at precipitation, it's more what I said earlier. Depends on which scenario we follow. It's not intensive, but basically the wet regions are likely to get wetter. It's likely to lead to significant issues. Also, number of heat waves is likely to increase dramatically. Warmer temperature is likely to increase in most parts of the world. Impacts. I already mentioned the precipitation is coming more as larger precipitation events. That's also likely to continue. This is an analysis that actually one of my undergrad students did on the paper. Okay, sea level rise. We have about 8 inches of sea level rise, 27 meters, since the beginning of the 20th century. And sea levels continue to increase. Over this coming century, the rest of this century, we expect to see about another 1 to 4 feet of 3/10 of a meter to over a meter in terms of change. But it could be different than that. It could be more. Probably not too much less than that, but it could be significantly larger. Everything depends on what happens in order to increase. If you look at the sea level rise, the biggest changes have been in the Western Pacific, in this region. And so sea level rise in particular is significant in Taiwan and other parts of the Western Pacific. But the levels of sea level rise is very interesting. As the amount of carbon increases in the atmosphere, about 25% of that carbon goes into the oceans, where it turns into carbonic acid. It makes the oceans less acidic. As a result, it makes the oceans less basic, more acidic, less basic than they are compared to the basic side. But the acidification of the ocean is already having an impact. And the study that some of the laboratories from around the world indicate you can have a significant effects on shell life and other types of life forms in the ocean. And in fact, I know in some parts of the U.S., we're already seeing these kind of increases occur in the shell size of the shell. Increased acidification is also a significant problem, particularly for the Western Pacific, and could be a significant effect not only on the ocean level, but also on the coral reefs as well. Well, the impacts of climate change are seen across many important sectors. So I mentioned in the National Climate Assessment, we looked at a broad range of different sectors, including developed water, agriculture, energy, transportation, number of others. And we're already seeing impacts in all of those in the U.S. and we're seeing improvements throughout the world. If you look at the IPCC as well. One of the issues with sea level rise is that you get a storm surge, you get saltwater intrusions and respiratory crops. And this is an example of this shortage of southeast U.S., but you get similar effects. Likewise, this is another direct from the National Climate Assessment. Ecosystems in the tropical Pacific are being affected not only by sea level rise and acidification, but many other aspects of changing climate that are also potentially affected. Bottom line is that the larger the temperature change, the larger the impacts that are likely to occur across almost all of these sectors. Future climate change really depends primarily on our choice about emissions. And we're going to take a quick look at what we can do in response. There are many actions we can take to reduce future climate change and its impacts and prepare for the impacts we can't avoid. That means both mitigation and adaptation. Mitigation is extremely important in terms of reducing those emissions, avoiding those highest level of effects on climate that I mentioned earlier, at least reducing the smaller effects. But nonetheless, adaptation will be very important. As an example, responses for the first of the U.S. As part of the analysis of risk management, one needs to consider the perception of risk from the public. Not for that, because this is an education model to teach the public what is going on, but also develop the right kind of assessment and the process to deal with the changes occurring in climate. We have to realize adaptation is not a choice. These are some of the conclusions from the adaptation chapter of the assessment. Basically, mitigation and adaptation go hand in hand. We need to realize that the less we mitigate, more adaptation will occur, need to occur, and also that adaptation is affected by many other stresses, also affecting those different sectors, and we need to account for that as well. There's a process one can go through to look at adaptation, from identifying the risk and vulnerabilities, planning, assessing, and selecting options for responding, implementation, monitoring, evaluating, putting back your data, and revising on the strategy and starting this. That's going to be an important part of this process. We're not going to get adaptation perfectly the first time. In conclusion, this climate is changing. It's changing rapidly, and it's changing because of human activities. Our future depends on how we act to limit climate change. Mitigation is extremely important to avoid the worst of those changes. Adaptation is not a choice. The choice is whether to adapt proactively or respond to the consequences of severe weather that's happening. Adaptation requires a paradigm shift, focusing on managing risk. Planning is important. As humans, though, we can draw on our long history responding to changing conditions and facing the challenge of climate change. I feel a sense of hope that we can deal with this, and certainly I hope we will. But we have to all recognize we have a choice of what our future is going to look like. Not only our future, but the future of our children and our grandchildren, and those that will be on. So thank you all.
We have a few minutes for questions. Maybe two questions. Any further questions? Maybe I can ask one. You showed in the U.S. the heavy precipitation increasing. Have you been also looking at light precipitation. Change there.
The problem with light precipitation is the data. And models tend to way too much light precipitation and actually not enough heavy precipitation. So we can underestimate what we've been observed. With light precipitation, it just isn't as clear an analysis. Generally, you might expect that it would be a decrease, but I haven't seen that.
Thank you. Any more? Yes.
Yeah, sure.
I have a question about the changes. I know that you come from and you had we depend a lot on and I know that actually
One of my former students, Captain Cable, Texas Tech University, led an assessment for the state of California. And one of their findings was that you can expect there will be less precipitation coming in snow. Doesn't mean you won't get snow, but then you know, now, the severity of events means that you can have large precipitation events, you can have large snow events as well. We talked about in the Atlanta area, for example, had snow again a couple of years ago. And that type of that happened just before we had the American Democracy Society. Those kind of events are going to happen in the changing climate because you get the right conditions for very large snowfall, very sudden. However, in general, we expect California mountains to have less snow, and that means that it's going to be important for this, that state and some of the other states in the West to really plan around that to better job of gathering the rainfall that we get in these basins.
Next, Paul, and let's thank Professor Walrus again. Thank you.
Okay, let's welcome another Nobel Prize with honor. Dr. Sheldon Liu, please. You.
Thank you for very, very effective introduction. Actually, I worked at NOAA for after when Dickens here. Actually, I worked at NOAA for 18 years. And in that time, our office and I worked in the same area for a long time. When the stress during ozone, I shifted quickly to the total spread and fusion problem. And came back to Taiwan 15 years ago. And since then, I've been working on climate change problems. The title of my talk is Adaptation to the Impacts of Climate Change in our Pacific regions. And for our area, I think the most outstanding, one of the most outstanding problems is we worried about how typhoons or tropical cyclones are going to change this global warming. And shown here are tracks of tropical storms observed in last 25 years. And you can see that for our area, you know, in the Pacific area, nearly or more than 2/3 of the tropical storms occur in our area. And if the heavy precipitation from these storms increase this global temperature, then we could be in trouble. If that happens, it could be the most important task for us in the Pacific area to enact adaptation policies. Talk about IPCC reports on extreme precipitation, and oops. The pointer is getting weaker and weaker. The gross report says the extremes are likely to be more extreme. But if you look at it in detail, IPCC report has been very, very conservative on extremes. And in fact, the one this meeting has been leading is even more conservative than 2007. I don't know if you admit that or not, but I think that's the fact. And so it's so conservative that you can hardly see any projections for future change in extreme precipitation events. We did some work in 2009 GRL. We suggested just a little paragraph because we were working on the precipitation, not just tropical storms, but also heavy precipitation in general. And we made the analysis of the data over the last 50 years, and we found that heavy precipitation, up 10% heavy precipitation associated with typhoon, increased by more than 100% for just one single degree increase in global temperature. And at that time, nobody believed us. And I regret to say, even today, there are not too many people agreeing with us. But nevertheless, my colleague in Taiwan, by last 2 years, they also found the same thing we found, except they claim that we were wrong anyway because we said that it was associated with global warming. They give a different explanation, and most of it was some kind of dynamic, thermodynamic explanations, such as changing tracks, and some of them, or most of them, claim that the typhoons probably the translational speed that has been slowed down. And that's a very nice explanation. But actually, even today, we think that that's not true. Okay, I'll show you. In the following, we are going to do an analysis that we are going to look at each of the typhoons during 1979 and 2007. During that time, we had satellite data. We follow every single typhoon in the world, and we go a circle around the circle of the circle of typhoon, the circle of 750 kilometers, and we find precipitation associated with typhoon, the all the precipitation in that circle. Here's one example. We have quite a few tropical storms here. One here, one here, another one here, here, and we just along the track, even with all of this. And we did the annual integration. Shown here is the top 10% annual precipitation, heavy precipitation, top 10%, and associated with typhoon. And we try to relate to the tropical ocean, global tropical tropical temperature. And we find that a positive correlation. The p-value, p-test actually is not bad at all. But we can increase this by doing the so-called interannual difference lesson here, only about 36 or 37 years of data. The interannual difference and interannual difference of temperature get much more independent data, and here's what we get. For top 10% heavy precipitation, okay. Now we slow. You see the slope of the p-value instead of 0.04 is much less. So the significance of the slope is statistically is very good. And the slope of the heavy is 200. That means temperature increased by 1 degree. Tropical temperature increased by 1 degree. The top 10% heavy precipitation is going to increase by 200 times per second. That means 1 degree change in tropical temperature would give statistically the top 10% associated with tropical storms, heavy precipitation would increase by 200%. That's really alarming. And we also notice the light precipitation associated with typhoon. By the way, typhoon would become everybody in Taiwan knows typhoon. We all say it's very heavy precipitation. Actually, typhoon also brings along moderate and moderate precipitation. The lower temperature actually increases. And the slope is not small, it's 7%. We did this first for northwestern Pacific in our area. And we also did, after we did the top 10% and the lower 10%, we also looked at the other category of intensity. Showing here again, the top 10% heavy precipitation increased by actually 210% for 1 degree increase, 1 degree K increase in tropical temperature. And look at here, all the light precipitation and moderate precipitation increase. And so this decrease substantially is the average of 50%. We did this figure for global all the tropical storms, including those in the Atlantic Ocean, and we found in fact, an increase, including all the storms, the actual increase of 100, 210, 225, a little bit increase. Anyway, the important signal is not 10%, any precipitation associated with tropical storms increased by more than 200%, for just one single degree increase in tropical temperature and lightning and tropical precipitation decrease. And in order to show our colleagues who relate the translational speed of typhoon that we decreasing, that turns out to be correct for Taiwan, but it's incorrect for the global translation of speed. Of course, it's slow. You can see it's decreasing, but the P value is very high. So that slope is no difference from here. The increase of heavy precipitation from tropical storms could not be because of change in translation of speed also. So that's our conclusion. I'm going to read it again. We believe the change. We will say this. Between 79 and 207, the temperature increases around 0.4 degrees, and 0.4 times 200% is around 90%. In other words, just see that for 38 years, the tropical storms, heavy rain, already increased by 90%, almost a factor of 2. Yeah, that's for the global and similar changes. The most specific Taiwan area. And this kind of increase is consistent with the theory summarized by Flinders and all in the global study. Essentially, it's what increase in the tropical storms. As you know, the water vapor will increase by about 7%. The heavy precipitation obviously increased by many bigger proportion, much more than 7%. And there's no significant change in the translation bring the question back closer to home. This is for Taiwan area, and now the figure I'm showing is for all the precipitation, including tropical storms, but also including non-typhoon precipitation. The top 10% increase now is at a smaller measure, but it's still very surprisingly large, 120%. Light precipitation decrease. The important thing is what happens is light precipitation is shifting heavily, and the decrease in light precipitation also shows up in the increase in annual total dry days, and that's I think that's reasonable for for that to happen. And when we thought that if we really look at the extremely dry case, that the situation that continues 14 days without rain, look at that, that's an increase. And between 8 and 14 days, the increase is like 30%. And that means in Taiwan, not only we get more potential flooding type of heavy rain increase there, but in terms of risk of drought, there's also increasing. And I guess that feels like a long time, but nevertheless, this is last week's here is a very slide. Here, actually, various methods, and also some most important agricultural and industrial area, China, and Eastern China, heavy
你是进哪一个孔？它就这里。是谁？
There's a lot of you see that has been reduced and Friday so there's an increase in risk. And this is
那现在是
problem
有点远麦克风，
result.
应该是要在麦克风去设计。
One of the reasons, of course, is that so much of this, with some of the moisture of the water, but another important thing, was this so-called water vapor lapse rate climate feedback effect that increase the temperature in the upper troposphere and compared to the lower troposphere, such that there's an inversion, temperature inversion sort of that making the atmosphere in general more stable. And stable atmosphere affect the light and moderate precipitation more than the heavy ones. We see that both increase the dry days and reduce the light
moderate rain can, can increase the risk of drought. And couple that with the increase of heavy precipitation in the Pan-Pacific regions, we believe that adaptive actions, including flood and drought control, prevention, and maybe more importantly, water resource management. Now water resources are in short nearly everywhere in the world. In Taiwan, we get 2,500 millimeter per year precipitation, but actually Taiwan's industry is suffering very, very severely from water shortage. Simply because we have such a dense population and the industry and the agriculture that rely on water heavily. And the last and maybe even more important, actually, for places like Taiwan and maybe more so for like Philippines, the land use adjustment are very important. In Taiwan, there are still a lot of people living, Aborigines living in the mountains, and when typhoon comes, the precipitation in the mountains can be very, very dangerous. There's a lot of landslides. So there's really important we reconsider how we develop the mountain area. And with that, I thank you for your attention.
Just actually, you can use Chinese to ask questions. We have the translators here. 你可以用中文，没关系，我们后面有及时的翻译。Sorry, please.
Xiao, thank you. It was a nice presentation. One of the things I did not get to mention is in our analyses, the projections for the future for the U.S. showed that in between rainfalls, we get more dry period. So much like what you were seeing already, which we're not seeing as much yet in the U.S., is something that's really projected for the future, that we would expect that you get large rainfalls and then in between you might get a small drought, and which is really great for farming.
Yeah, that's very consistent with what we saw. So for that, for Eastern China, it's large, almost half of China, we saw the same thing. The annual average dry days in Eastern China 50 years ago, it used to be about 220 days. 7.5 months, okay, dry days. Now it's 8.5 months dry days. So when I show this to my Chinese colleagues, they say, "Oh, you're wrong. We know it had to do with El Nino. After a few years, our dry days will come back. I mean, I'm already will come back." Well,
Yes, please.
Congratulations, that was an excellent presentation. And I following on the previous question, just a clarification that you're seeing increases in both the frequency of dry days and also the duration of consecutive dry days.
Yes, correct. Total number of dry days per annum in Taiwan is about 210 days. And that has increased to 235 days. Increased by 25 days. Yes.
Thank you.
Hi. In terms of the climate summit in New York last week, just closed, and what kind of adaptation measures you expect Taiwan government to do or develop for the COP21 next year? Thank you.
You talked about the climate convention that started in the U.S. in New York last week. That convention, I believe, mostly to do with mitigation and the reduction of emissions of greenhouse gases. But of course, adaptation is also important. And mitigation, of course, is the most fundamental process we need to do to reduce this. But that takes a long time. In fact, the CO2 already in the atmosphere, the decay time, the half-life decaying time for CO2 already in the atmosphere is about years. And that means whatever happened showed by Professor Wobbles, whatever will happen in the next 20 to 30 years is going to happen. It won't change at all from any mitigation, okay? And that means we have to do the adaptation. That's already, climate change already happened. The temperature in the last 100 years or so increased by like a 0.8 degree. That's very close to what I said here, 1 degree, okay? So climate change has already happened and it's here. And will stay with us for another at least 20 to 30 years, no matter what. So, living in Taiwan and precipitation increasing almost by 100%, we really need to carry through adaptation policies.
One question.
What's your exact mathematical modeling for the increase of the degrees and the precipitations in Taiwan? I think you're trying to show a lot of figures about modeling. And I also have another question is, you show that the average speed of the typhoons is decreasing, right? How about the life cycles of typhoons? Do they exist a bit longer or shorter?
We did look at the. Let me answer your last question. You talked about the frequency and all those, and the duration. We looked at all those parameters. Frequency has been decreasing. Okay, that's very clear. The number. Okay, and the duration multiplied by the frequency also decreasing because the number decreases so clearly. Answering your first question, say what does the model say? Okay, let me first backtrack a little bit. Theory and model both say the total precipitation increase slightly. 1 degree increase in temperature. The total precipitation global-wise increase only by 2 to 3%. And the model theory both agree on that. But on the heavy precipitation, the model also says would increase, but the increase is like 10%. The top 10% precipitate increase only around 10%. Okay, and the light precipitation decreased by like 2%. Essentially, a factor of 10 lower than what we see in the data. Okay, the model agree with the data in terms of direction, but in terms of magnitude, it's much smaller. I don't know why, but yeah. In fact, I think Dr. Higgins may be able to address that problem.
Hello, sorry, Dr. Lee, please.
I'm Nhật. I'm from Vietnam. I'm working on the department on climate change adaptation of Vietnam. Thank you very much for your lecture. Also, what did not question, just explain more about the rainfall and some comment on this study, because we talk about the extreme event and we talk about the rainfall, but actually what I'm thinking is that change, but it change frequency and change area. I mean, we should link between the duration, frequency, and intensity and area. It means that the change location about the rainfall. Is this exactly for the study to thinking about the climate change? Because this study is just already tell us about the extreme event. We're concerning about just already the data from rainfall from the extreme, from the storm and flood and extreme event. But how do you think about the link with each area and the rainfall of the each area? And we can summarize something on that.
Okay, earlier, when I answered the earlier question, I did say the total rainfall, the change in different regions tend to be very small, okay? And that's consistent with theory, with model result. The total rainfall, I mean, there's a lot of study on total rainfall, how much increase in Taiwan, in the US, and for example, one very clear trend mentioned by Professor Wobbles is southwestern US in the maybe 50 years have been, the total rainfall has been decreasing. That's statistically very clear. But for most regions in the world, it's very small, the total rainfall. And it's very hard to any clear trend. For example, in Taiwan, last 50 years, there's hardly any, even 1% level type of change in total precipitation. Okay, there's a little bit regional change. Southern part, it decreased a little bit. Northern part, it increased a little bit. Overall, there's no change, essentially, not even 1%.
Okay, thank you very much. Okay, thank you, Dr. Liu. Thank you very much.